Hello everyone, I'm Arjun, and today I'll tell you about BurstTracker, a new tool we developed for determining whether or not LTE is the bottleneck for your mobile application. This is joint work with my collaborators at Stanford, UHANA, and UC San Diego. Now, to show you the problem that this tool is addressing, let's take a look at a typical scenario showing how developers today diagnose poor network performance on cellular networks. Here's a video streamed on a phone over LTE. Imagine you're an application developer. You notice the video is being streamed at 360p. The quality is so poor. This seems to be due to poor network conditions. The video used about 1.5 megabits per second. What do application developers do today? Well, they have a problem and they run a speed test. So we run a speed test and get a throughput of about 10 megabits per second. What's going on here? The speed test says that the video could have streamed at a much higher quality. The problem is that we can't conclusively determine if the cellular downlink is the bottleneck for this application. That speed test does not tell us why the video streamed poorly. It could be, for instance, that congestion at the radio link stopped when we started the speed test. Or perhaps the speed test was given priority. We just don't know. This is the problem that we tackle with BurstTracker. We'll show you, using BurstTracker, why this disparity existed for video streaming later in this talk. We actually found that the bottleneck was surprisingly not at the LTE link, at the LTE base station. It was somewhere else. So we said that speed tests don't work. Let me now explain why. Let's say you're an application developer and you're trying to diagnose the bottleneck in your application. Here's a typical network topology for your mobile app. Well, the bottleneck could be slow code at the application server, throttling somewhere in the carrier's network, congestion at the radio network, or slow code at the client device itself. We could devise workarounds for most of these situations, except for when the bottleneck is at the base station. So what we really need is a way to determine whether or not the bottleneck is at the radio link. But what things do you as an application developer really know anything about? People have developed many tools to debug most components of this picture, from profiling the application to identifying middle boxes in a network. But developers have no visibility into the radio link. And when we see poor application quality, we just assume that the radio link is the bottleneck. If we can't know for sure whether the bottleneck is in the radio access network, we don't know to look elsewhere. I'm going to show you a new tool, BurstTracker, that allows developers to conclusively factor out the radio link before shifting their debugging efforts to other parts of the network. So what do we need to know in order to determine if there is a bottleneck at the cellular link? We should know the status of the queues at the base station. If the queue is empty, then we know that traffic is bottlenecked on the way to the base station. And if the queue is not empty, then we know that the application is sending enough data, so the bottleneck must be at the base station. The reality is that providers know the status of the queues at the base station, but no one else does. In this work, we solve the problem of identifying the bottleneck by revealing the status of the queues using data that is already accessible to application developers. But how can we infer the status of the queue from the client device? Thanks to recent diagnostic tools like Mobile Insight, a user can obtain its resource scheduling information from the client side. Let's now see how we can estimate the queue status from this data. This is the really big insight of our work. If you look at how traffic is scheduled on an LTE network, base stations tend to schedule one user at a time. To visualize this, I'm showing you a capture of the traffic scheduled on a real LTE base station in a very congested area. On the x-axis, we have time, and on the y-axis, we show the number of resources scheduled. The color corresponds to a unique user. So for example, this purple column shows the resources that were scheduled to the purple user in this particular millisecond. Now, just to prove to you that we're showing real data that we passively sniffed from a real base station, for various reasons described in the paper, there are holes in this data, shown here in yellow, that are due to decoding errors. So in the snapshot, we have two users being served by the base station. The pink one is doing a large persistent transfer, and the purple one is doing an intermittent transfer. There are two users here contending for the same resources on the base station. Let's focus on the purple user, for instance. Notice that in most time slots, such as in this one, the base station gives all resources to a single user. This is a signal that the user's queue is not empty. So then how do we know if the user's queue ran empty? Well, if it ran empty, perhaps another user got scheduled. Let's look at this example. Notice that the pink user got scheduled in the middle of the purple user's transfer. So you might think that the purple user's queue ran empty. But the key thing is that in the previous millisecond, the purple user had enough data in its queue to fill up exactly all resources in that millisecond. So it's very unlikely that its queue ran empty at this point. It's just that the scheduler had to swap in the pink user for fairness. Let's keep moving along on this trace. Notice that the pink and purple users were both scheduled in this millisecond. That is an indicator that the scheduler ran out of traffic to give to the purple user, which means that its queue must have drained out. Using these signals for the status of the queues at the base station, BurstTracker identifies the periods of time when the queue is not empty. We call these periods bursts of transmission. Now notice that with BurstTracker, a user only needs to know their resource allocation to infer their queue status. And as I mentioned earlier, fortunately, there are tools to obtain this information at the client. Okay, but this is all based on one fundamental assumption, which is that the base station will only try to schedule resources to one user at a time. In the paper, we discuss why schedulers would try to do this, and there are plenty of good reasons. So the question is, does this assumption generalize? We designed an experiment to see whether or not this behavior was happening on schedulers belonging to different carriers over a wide variety of load conditions. In the paper, we show results for 3 carriers, Verizon, AT&T, and T-Mobile. For this talk, I'll just show you the results for one provider, Verizon. So here's the experiment. We sent a very slow stream of data at 1 megabit per second and looked to see the resources that were allocated to the user in each time slot over the stream transfer. And that's shown on the x-axis. We're plotting here a distribution of the resources allocated in each time slot. If our theory holds, then we should see that at a lot of these time slots should have many more resources than what's required for an instantaneous throughput of 1 megabit per second. In other words, our distribution here should be weighted to the right of this 1 megabit per second line. Shown here are distributions for Verizon for both an idle cell and a busy cell, since the load conditions may change the scheduling behavior. What we see is that in both cases, even though we are trickling data at 1 megabit per second, very rarely are we getting a few resources scheduled in each millisecond. And often we are getting allocated resources at a much, much higher rate. In fact, the scheduler used so many resources that it had to use several MIMO channels and carrier aggregation, including resources across 2 base stations, to deliver this traffic. Okay, we've shown that our assumptions are all valid. One final question that we must answer is, how accurate is BurstTracker in estimating the queue status? To do this, we partnered with a Tier 1 provider to get ground truth measurements of the queue status for 100 file download and 100 video streaming applications that we ran. This table summarizes our results. BurstTracker isn't perfect, but it works pretty well. It achieves a median error of 7% in estimating the queue status. Let's now return to the example that we looked at the beginning of this talk. This experiment quantifies that example in more detail. We ran a speed test, then streamed a video and recorded the throughputs for each segment download, and finally ran a speed test at the end. The question we asked at the beginning was, why was the video streaming application's throughput so much lower than the speed test throughput? I'll now show you how we used BurstTracker to find that the LTE downlink was surprisingly not the bottleneck for video. Let's zoom into a single video segment to understand this further. We started by verifying that it wasn't the server. In fact, the video server pushed the video segment out in 25 milliseconds. But as you can see here, the client received the segment data over 700 milliseconds. What I'm showing you here is the LTE resource allocation for a single video segment. The x-axis is time, and the y-axis is the fraction of resources scheduled in that millisecond. We ran BurstTracker on this video segment trace. Here are the bursts. BurstTracker tells us that the queue is running empty a lot. In particular, look at the duration of the bursts over the video segment download. They increase over the entire segment download. This behavior is characteristic of TCP slow start. But we followed the HTTP specifications to disable slow start restart at the video server. So it is likely a Middlebox somewhere in the network. Through additional experiments, which are described in the paper, we verify that a transparent TCP proxy on all 3 Tier 1 US carriers appear to be forcing slow start restart and causing video streaming applications to underutilize the cellular downlink. We ran an experiment to quantify this. For each carrier, we streamed 25 videos each over HTTP, HTTPS, and a non-standard port, through which we can bypass the Middlebox. For each video session, we use BurstTracker to compute the percent of the time the queue is occupied, and we report this as the link demand ratio on the y-axis. We show HTTP in red and HTTPS in blue, and you can see that for all 3 carriers, the queue remains occupied much less than 70% of the time on average. And we show the non-standard port here in green, and you can see that the video stream is able to use 40% more of the link. We also observed that the bit rate streamed was about 35% higher on average. Now, to summarize, we started with a common problem where video streaming was performing poorly and speed tested and explained why. To solve this problem, we built BurstTracker, which allows developers to determine whether or not the cellular downlink is the bottleneck. And our algorithm was driven by the neat insight that we can infer the queue status from the way the base station scheduled resources. And we applied this to video streaming to discover that a Middlebox in the carrier's network was forcing slow start restart on video segments. Thanks, and I'd be happy to take any questions.